We have been busy collecting data over the last couple of years, and that's what we are here to present to you today. We've got a full agenda for you. The background we'll touch on, pretty much focusing on why it is that we did this study. And then we'll dive into the current demand response opportunities as we sit here today, and looking out into the future a little bit with some more advanced technologies. We're also going to basically align these demand response opportunities to the bulk power system services that our grid is ever changing and ever needing new types of demand side resources in order to address an increasingly complex bulk power system operation, as well as distribution system operation. We're then going to categorize each of these end uses and enabling technologies in a framework that matches to the demand response opportunities and also to bulk power system services. And then we'll briefly discuss the framework for the enablement cost, including the components, what kind of makes up enablement of a site for participation in demand response. And then finally, we'll get into the details of how much it costs to actually install and enable demand response technologies at a specific site or by customer sector. And without further ado, we'll jump into the background. So the objective of the research that we conducted here is we wanted to organize and present a framework and quantitative assessment of enabling technologies by end use that could meet a suite of services or provide a suite of services based on the needs of the bulk power system. And in particular, focusing on local resources. Typically, demand response has been deployed so that it can meet, bulk power system needs. As we're finding throughout our research, and as practitioners at both the utility and in academia, we're finding that we need demand response resources and demand side resources to be more locational, and we need to start thinking them in a way that they will specifically address needs of the grid. So rather than it just being a bulk dispatch of DLC, of direct load control units to address peak capacity system constraints, we have started to branch out from that very narrow examination of demand response and start to examine it in a framework that allows demand response or examines and assesses the ability of demand response to meet more than just peak capacity needs. So this is not your father's demand response. So we've defined demand response as a mechanism through which an end use's load profile can be changed. And that can be done by the user. It can be done through an aggregator of retail services. It can be done through the utility. But it's in response to the system needs, and often this is in return for economic compensation. So it can be either a rate structure or it can be an incentive payment, and depending on the state, those are set up, and within the United States, that can be set up fairly differently. But we did look and find some consistencies, really looking at stepping back and saying, what are the universal questions for demand response? What is it that we're trying to do with the resource, the demand side resource? And the first question that comes out of that is, what does the bulk power system need? And then moving along, what kind of role can a demand side resource or demand response resource play in meeting that need at the bulk power system? And then finally, of course, very important, what's the value proposition? How much does it cost to enable that resource? And then what's it worth to the grid and to the consumer? When we start asking questions for demand response in this manner, we get some answers that are a break from conventional thought. And primarily one is that the electric grid may not need just peak capacity DR. And so when we start evaluating the different types of technologies, we should be thinking about them in a manner that that looks at what other kinds of services that they can provide to the distribution and bulk power systems. So why is this important? What are we dealing with here? This is driven truly by the challenges of a dynamic grid. We have increased penetration of renewable and distributed generation throughout the country, not just limited to California, which is this infamous duck curve is taken from. But these produce challenges of ramping, where we have morning ramps down as solar generation comes up, and then we have, of course, the evening ramp, which is typically exacerbated by an evening peak. You have curtailment of renewable resources, including wind and also solar, during the middle of the day because we just have more resource on the grid than we actually have demand. And then, of course, you have inter-hour variability. A lot of this comes from, even retirements of thermal loads and thermal generators, where we're seeing more of those retired. We're relying more on intermittent renewables, and so you have the short duration ramps during the middle of the day that create some challenges to managing this. So we really do want to think about looking at something other than just supply side resources. There's a question of, we do spend a lot of time in our industry talking about how we're going to meet the grid needs and provide service to these customers. But the reality is that we have two sides of the coin here, and one of them is demand side resources, and we can do a lot to manage some of these challenges on the grid by using demand response. One of the types of demand response is time-based rates. In our study, we've categorized these as two different really kind of structures of demand response, one being time-based rates, the other being the incentive-based programs. Time of use is very well known. It's gaining a lot of traction. California is moving to a default time of use rate throughout the state, of course with an opt-out component. But these rates provide different but predetermined prices over specific temporal periods. Critical peak pricing is very similar, but it's set with typically very high price ratios between on-peak and off-peak periods. It's a narrowly defined period, and it's typically constrained to be called only and dispatched only a few times a year. Most typically around 12 times a year on the hottest days, or the days where system operating conditions warrant it to be dispatched. Variable peak pricing is very similar to critical peak pricing, except that peak period price, that price ratio, can change from one day to the next. So it doesn't have to be necessarily 75 cents per kWh every hour that it's called or dispatched. And real-time pricing is not a dispatchable program as of yet. Typically, customers are given price schedules 24 hours in advance. Sometimes, in some cases, the prices are provided to the consumer 60 minutes after the consumption has occurred. So it's not necessarily a dispatchable type resource. So we really do, within this study, focus on dispatchable resources. And that takes us to incentive-based programs. So from the previous slide, we have critical peak pricing and variable peak pricing, which are dispatchable. And then here we have controllable and configurable type DR opportunities that are also dispatchable. But I'm going to run through these because we have in this paper attempted to simplify some of the language that we use around these types of programs, and then even the bulk power system services that they provide, because it's cumbersome and there's a lot of different variations of the same kind of ideas and programs that are out there. So we first defined controllable as a type of DR opportunity where the utility or an aggregator, and even in some cases an ISO or RTO, independent system operator, regional transmission operator, ISO, RTO, have the ability to directly control a customer's end use in their electricity consuming devices. It can be increased, it can be decreased, and it's usually done with little or no notice. So this is a fully automated type program. and similar to the controllable would be configurable, which is the same type of idea, except that the customer can override or they can configure the control technology after a dispatch has occurred or even before if they have advanced notification. For example, if there's a programmable communicating thermostat program and the utility triggers an event to change the set point on that thermostat, the customer typically has the ability to go and override that control technology. So they can say, nope, not today, it's too hot. I'm going to turn that back down. I want my house at 70 degrees. So that would be a configurable type program. So in this case, that means that that type of resource is not necessarily guaranteed as 100% available. So whereas controllable, you know exactly how much you're going to get, it's given that the device is actually on. Whereas configurable, the customer has some control over that. In the case of a manual type DR program, this is really common in the industrial sector where there's process loads and pumping loads that can be modified, turned down, ramped up, and this is done typically through a phone call. Hi, we need you to change your load profile at this point. Do you have any discretionary load that you can shed? There is a financial payment typically associated with these manual type programs, not in all cases, but typically. And then the behavioral component, there's no explicit performance payment, but this can be thought of as something like Flex Your Power, which is California's behavioral program that tells customers to eliminate any discretionary load, but there is no financial payment associated with that. So for the purpose of our study, we do want to focus on only those dispatchable and controllable type programs. So here we've listed these out. So this is a subset of the DR opportunities, and they have a unique number, they have unique characteristics associated with each class of the rates or the programs, the incentive programs. And these are basically categorized as the advanced notice of a dispatchable event signal, the maximum duration of an event, and the frequency of those responses of the dispatchable events. So those details provided here for this is pretty typical of the parameters that we've defined within this slide. This would be a pretty typical parameter for programs within the U.S. And great. So now we want to match those dispatchable type programs over to we need to dig down so that we can start understanding what types of programs and demand response opportunities can provide bulk power system services. And so that's where we're going here in order to identify some of the costs here, because we want to look at the value proposition. So what we've done is we've taken this long and lengthy list that's still fairly condensed given the complexities of the bulk power systems in the U.S., where we've identified some higher levels: spinning reserves, supplemental reserves, imbalance energy, resource adequacy. And we've mapped those over along with their time scale, and we've filtered those over to those parameters that we defined in the previous slide for each of the programs. And we've identified which type of DR opportunities can be mapped to those bulk power system operations. And as you can see, anything that's controllable truly can provide, because you're taking sort of that human component out of it. It's fully automated. They're able to provide the majority of the bulk power system opportunities. And in this case, we've indicated that they do all. For the time-based rates, they're fairly limited to day-ahead energy and resource adequacy type resources. And for configurable, you can do hour-ahead and multi-hour ahead, and so which is basically same-day dispatch for those types of resources. And so given this last slide, there's a whole lot to analyze here. So what we've tried to do, and what we did in hopefully many of you are familiar with the 2025 California Demand Response Potential Study. we looked at all of these different bulk power system operations and services and said, wow, that's a lot. How are we going to match every end use to each bulk power system operation? So what we did is we boiled this down and to a portfolio of services that can be considered for a more generalized purpose and a friendly nomenclature. So less jargon. We're still capturing the very essence of the different parameters and requirements for each of these bulk power system services, but we're able to do it in a way that allows us to communicate it more succinctly and also takes away some of the heavy technical terminology. So within this, we have defined shift, shed, and shimmy, which are our favorite terms, mine at least now. So these resources stack a span of a range of possible electric grid needs. So this can be addressed, by shift, which is something that can be handled by season, and also to seconds. So shift is your load that can consume during the day or in the evening hours, and then it can also shed load over a 24-hour period. And the remarkable thing about this resource is that it remains energy neutral. They're based on end uses that can take discretionary load consumption from 1 hour and move it into a different hour. These have pretty significant value for reducing overgeneration during hours of high renewable generation and avoiding some of the multi-hour ramping needs that you would see during the day, during those morning and afternoon hours. There's second is your shed type resource. Shed is your conventional DR where you're dispatching for many hours during the day or a day ahead in order to manage forecasted peaks or contingency events. It can include fast shedding resources that can meet local capacity needs or distribution system needs, and it is one of those resources that's very valuable for emergency conditions. So I know that California in this year had called its very first shed event it was about 10 years since they had actually called some base interruptible programs and some capacity bidding programs. So it's one of those that even though it may not be used frequently, it can be very valuable when it's needed. And then finally, we introduced this resource that's called Shimmy. And Shimmy is our fastest demand response resource, and that operates in seconds to minutes, which would be regulation type services, or minutes to hours, which would be a load following resource. And so that would handle some of the intermittency throughout the day. The need for Shimmy is really bounded based on the variability of the net load. But it does have a high value in maintaining stability and managing short-term fluctuations, primarily during those inter-hour ramps. So the next step for us was to take all of that wonderful information that we had on the bulk power system and then each of the DR opportunities and then map them over to our service types so that we could start thinking about the different types of technologies that could provide shed, that could provide shift, and that could provide shimmy and meet some of these bulk power system services. So this was, we mapped together the system services, the opportunities, and then our new nomenclature using a more simplified framework with shed, shift, and shimmy. So this takes us to categorizing our end uses and enabling technologies. Primarily we need to build a framework for each of the end uses in the sectors that we evaluated under this assessment. We looked at commercial, residential, battery, electric, and plug-in hybrid vehicles. A lot of the technologies that you see here are either automated demand response or advanced demand response. Automated demand response, direct load control, which is still nice and viable option for utilities, and they're still pursuing that. and then the programmable communicating thermostats. In our analysis here, we took the study results from the demand response potential study for California, and we expanded those results to encompass a more national cost framework, as well as including some more applicable end uses in the analysis, such as hot water heaters. Obviously, this is not an exhaustive list, but the idea was to at least begin capturing some of these costs in the range of end uses and technologies that can help provide bulk power system services. And so next, what we're going to do is take a deeper dive into matching these end-use, sector-based enabling technologies to this bulk power system services that they can provide. And this is an exercise that was pretty important because it shows that there's some limitations to each of the technologies that in providing services. Some of them just aren't advanced enough and flexible enough to provide some of these faster response type services. Some of them have been built out to truly focus on peak capacity shed type resources, and you can see that here in the residential sector where all of the technologies can be shed. And this is a result of our industry having focused on shed for a very long time, and there's value in that. I'm not dismissing that, but it does show that we have technologies and enabling technologies, advanced technologies that can do more than just shed load. And shift, if you recall, is the ability to increase load during a part of the day and then shed it at a different part of the same 24-hour period. So some of those technologies that can provide shed can also provide a shift type resource. The exception is the direct load control switch. It has no load building functionality, so you can't pre-cool or turn it on, turn on an end use. But for programmable thermostats, and in the case of electric hot water heaters, you actually can use these DLC switch. They're what I call advanced direct load control switches. They are retrofitted onto electric hot water heaters, and they can actually increase and decrease load within, I think I've heard stories of 4-second intervals. So, so they're fairly responsive. And then, of course, batteries are the ideal technology that can pretty much do everything using automated demand response and smart inverters. And same thing with the electric batteries, the electric vehicle batteries and chargers. All right, and then the commercial sector, this is kind of a long list, 2 slides. So we have, HVAC, it's the same story there where the direct load control switches are not going to allow us to do any type of shifting service, but certainly can still provide shed. When you put a variable frequency drive, which is what the BFD stands for, if you couple a variable frequency drive with automated demand response on an HVAC unit in a commercial building, you can do shimmy. You can start doing some regulation and load following, fast response, demand response. So that's something that these advanced technologies, as we continue to kind of move through the next couple of years, we would anticipate seeing hopefully some future proofing with these demand response opportunities where we start installing some more viable and variable technologies such as VFDs. Lighting is also really excellent at producing shed, and this can be done with advanced controls, not sensors, but controls. We do need to put controls in there. And it can also do shimmy, and so this would be done in a way that would really minimize the impact to folks within an office building, in this case office and retail, so that it would be slight dimming or exterior lighting or something along those lines that could do those faster shimmy type resources. We did focus on 2 advanced lighting systems. This is the digitally addressable luminaire lighting system, and then a zonal-based digital lighting system. you can still have, in the standard lighting control systems with ADR technology, they can only provide shed to the bulk power system since the controls are not sophisticated enough to provide that dimming type functionality. The next slide, we looked at the electric hot water heaters. So this would be for small and medium commercial customers. These aren't large boilers for large facilities. But they, once again, can do very fast response, demand response. Same with refrigerated warehouses because they have that. Anything that really has that thermal storage capability is going to be able to, thermal or in the case of battery and electric vehicles, any type of storage capability. So they're going to be your more robust technologies that can actually provide more services to the bulk power system than your conventional shed type resources, such as DLC switches. All right, and then finally, finishing up with our industrial sector end uses. Once again, the industrial sector has a potential, an incredible potential for automation. In particular, if we can identify discretionary load, we can install things like variable frequency pumps, which is what that VFP stands for, and then along with variable frequency drives. When we start coupling those types of technologies with automated demand response, you start really opening up the world of demand response capability and services for the grid. And there's a value proposition, obviously, for providers as well as for the facility owners and industrial customers. The shift type resource is one that this is where in the DR potential study for the industrial sector, that's really where we found the bulk of the shift type resources coming from, these variable frequency pumps and drives on pumping and process loads when fully automated. That's a difficult task, though, so I'm not going to undermine the idea that getting industrial facilities to adopt automated controls is easy. It is not. They typically want to maintain their manual controls and participate in these kind of programs without that. But if we can get them automated, they have a lot of potential to provide a lot of service to the grid, in particular in the shift category. Great, and now we get into the technical stuff, so please don't fall asleep on me. And so this is the key elements that drive enablement cost. And so this is a framework that we have developed and modified here at the lab, working closely with Marianne Piet and her research around AutoDR and OpenADR. We examined the three key elements here. And there's some important distinctions that this framework brings up that exist between conventional demand response and the enabling technologies and advanced demand response technology infrastructure that can provide fast and flexible service. And one of that main driver there between a shed type resource and a shimmy type resource is that measurement infrastructure that's in the middle of the slide right there. What you can see here is a program coordinator can dispatch a signal, this is on the left-hand side, to a technology, to an end use, to a premise, and that goes over communication infrastructure. We'll dig into each of these in just a moment. That can be either dispatched to a gateway or to an end use at the load itself. There's the measurement infrastructure such as the metering and that gateway that sort of bridges the gap. And then there's the control infrastructure, which is the control logic within the enabling technology that's actually manipulating the load. So to dig deeper into this, we'll start off with the communication infrastructure options. So the communication, there are four primary solutions used to send a dispatch signal to the end uses or to an energy management control system at a customer premise. And this includes the FM radio or pager-based communication solution. It can include the Wi-Fi or broadband communication solution. Cellular is another viable option and increasingly popular. And then, of course, you can utilize the advanced metering infrastructure network communication. So the The components that receive the dispatch signals, it can be like the one-way communication with the FM radio or a pager-based solution. More advanced systems receive the signals and submit information back to a head-end system, which is a two-way communication system solution. And that can be through Wi-Fi, cellular, and even the advanced metering infrastructure, the AMI solution. Great. So the next chunk is that middle section that we talked about in the previous graphic. This is your energy measurement infrastructure options. And the slide on, or the photo on the left-hand side is of an electricity meter and a panel, obviously. This is this is the second group of components within the DR automation system. For the communication system to work, it encompasses electric meter or some other data logging resource, some other data resource, the communication resource interface, and then a gateway, typically, of measured data. This measures data and sends it back to the program coordinator. For the auto DR applications, the typical telemetry architecture includes several components. At the site level, a data collection mechanism measures the premise and end-use loads, which would be your electricity meter. And then you would have that delivering data to a resource interface, which is, for example, here in the network interface card. This is embedded in an AMI meter in many cases. And then that network interface packages and delivers that data over to a gateway, which is on the right-hand side. The gateway can either connect to a NIC, it can connect to a communication infrastructure or the meter. And the gateway packages and encrypts data using protocols such as DNP3-L2 over PKI. These are all really technical terms. But that data at that point is sent to the bulk power system operator or to an aggregator. You have several options for the electricity meter. It can be an AMI meter. It can be a high-resolution AMI meter, which would be tracking data at less than 5-minute intervals, 5-minute intervals or less. There's power quality meters, which are an advanced 3-phase meter. There's for the network interface card, or an option for the resource interface, you have KYZ module. This is a NIC card, which is an example. You can also use Zigbee. That's been proven to be fairly successful and can actually poll at less than 5 seconds. Most often it's around 10, so it can pull from the devices within the home. A gateway, typically it can be something as simple as a smart thermostat or a programmable communicating thermostat. That could be considered a gateway because it's communicating back to the aggregator. It can receive a signal, so it's already built in. In some cases, there's smart energy gateways. There is remote intelligent gateways. Those are all examples of it. But gateways are also known as energy service interfaces, and they're utilized in residential homes or customer facilities to connect to incompatible networks. So it's translating and facilitating bidirectional communication. All right, that was the most technical one. You guys ready to move on from that? So after a signal via the DR communication system is received, either through the gateway or it can be directly received by the end-use control technology, the signal is translated into a control action. For example, there's a number of different technologies that are capable of controlling an HVAC system in order to provide shift or shed services. They can include the DLC switches, which we discussed before, or automated demand response controls. The option of installing a programmable communicating thermostat can also increase the zone temperature or set point, and it can also decrease it for pre-cooling. All right, so finally we get to dig into the enabling technology cost assessment. So a couple of important things to note here. There's there's some costs that we did not include in this assessment. One thing it's important to note is there's going to be variability on the technology cost and then in the site-specific costs when you're installing this. And one really great thing to do is to do a Monte Carlo analysis that looks at some of the variability of that. That's not something that we did here. We took average costs for these technologies. We put them in 2017 real dollars. And basically have presented a structure of cost that gives us a benchmark and a starting point to understanding what it costs to actually go out to a site and enable these devices on end uses within a customer home or premise. The other thing that we did not include in this was operational cost. After the device is installed or after a building is enabled with demand response, any of the operational costs for maintaining software or the communication platform, such as a pager-based solution or Wi-Fi, those were excluded from our analysis because they are not the enablement cost. A next thing to consider is the attribution of the enablement costs, and this is really important. When we go out in the field and we install demand response, most of the time we're selling it under the guise of energy efficiency, or we're doing it to improve the performance of a customer facility. Now, this is important because people aren't going out and spending thousands of dollars just so they can participate in demand response programs. And so when we look at the cost here and within our framework, we are assigning the total cost of enablement to demand response. And it would be more appropriate in the future to take into consideration that customers are purchasing these end uses and devices, such as a programmable communicating thermostat. They're doing it to improve the comfort, to improve performance in their home, to be able to manage some of the energy costs, and to really optimize the service on their end of the deal. And they do get some incentives for typically buying that energy efficient component. But in many cases nowadays, we're actually throwing an additional incentive on top of that smart thermostat if they enroll in a demand response program. And so by doing so, we're saying this is how much incrementally it's worth to us to basically put that device into your home for energy efficiency, but also the demand response component, we're going to give you an extra kicker. So in the case of our analysis, we have said, here's the cost to install and put a smart thermostat into a customer home, with the assumption that all of that cost is attributed to demand response. Whereas we know, as I just basically explained, customers are doing it for a host of other reasons, so it would be appropriate to allocate some of the cost to those energy efficiency goals or comfort or non-energy benefits, and that's another study to be done. So, and then the last kicker and the last thing to think about here is the technology solutions for site enablement depend on what you're trying to do with that end use. So if you are trying to enable advanced DR and fast response services that can provide regulation and load following service under SHME, you're going to have additional costs that are associated with communication and hardware telemetry, and that you wouldn't have for just a shed component. And the reason for that is that for participation in these bulk power system markets, in order to verify that the resource is online and it's available and it's responding and it's a firm resource, you do have to have some more sophisticated telemetry and energy measurement. So that differentiates it from the energy services such as Shift, which we currently haven't identified a market where you're actually selling energy DR, demand response energy. So, but even as much, you're still going to need to have some different telemetry in order to capture neutral energy demand response, basically. So demand response that is energy neutral throughout the day. because it doesn't show up if you otherwise. The last one is your conventional DR services. This is, we've been doing this a long time in our industry, and we know how to do it well, and so those costs are typically, we know them what they are very well. We can use standard meters in order to capture that, that data that did the HVAC unit turn off. We can see it in load profile data. It's captured at the AMI meter or when we're billing it, and it doesn't require a whole lot of extra software, hardware, and communication in order to provide that service, with the exception of fast response shed. That's still going to need some additional communication and telemetry platforms. All right, so how did we organize this? So we went through this study, and we basically, for each of the end uses, we estimated the initial upfront enablement cost for a customer site or an end use based on the customer sector and the size of that customer. So in the case of commercial, it's small, medium, large. Industrial is in its own class, and residential is in its own class. So these include technology and installation costs, and are either provided as an aggregate cost in that it's a dollars per site. So it's the cost of enabling an entire site, or it's calculated by enablement cost per kW of load enabled to provide DR. And then lastly, we also have the cost to enable at the end use. So it's dollars per end use. And this is, for example, the electric vehicles and residential sector end uses. So you're going to buy a charger that has an electric vehicle charger that has capability in it that can communicate. It has the telemetry to measure load reductions and maybe increases. It can communicate directly back to aggregator or provider. And the same thing with the residential sector, and in particular, the best example is programmable communicating thermostats. So that's an end use. We're not looking at enabling anything per kW. And the extent for the commercial customers, we have looked at this as the variable initial cost for the control technology, because it's difficult using a framework to make apples to apples comparison for HVAC and retail lighting controls. We basically, in the industry, we do give rebates based on the dollars per kW reduction. And typically this is done as we go back and audit it and make sure that we are getting sort of this per kW reduction. And then we report that out as, you get $50 per kW for your load reduction. And so we mimicked that within this framework, also once again stealing from the California Demand Response Potential Study and Mary Ann Piet's work in categorizing and building an accounting framework for this. We found that the dollars per kW enabled is the best way to go for large commercial and industrial sites where these costs are variable. All right, and we'll kick off here with the residential DR site enablement. And I'm not going to spend too much time focusing or talking on every one of these because I'd like to get to some of your questions. But one thing obviously that pops out on this slide is, wow, that hot water heater with the ADR control is really expensive as compared to some of the other resources. And once again, this is dollars per end use. In this case, this water heater would be a full change out. It wouldn't be a retrofit. It wouldn't be something that you could, go and add an advanced DLC switch. Unlike it's a partner over there that is a DLC switch that would be added onto the actual component and end use. So that water heater in particular is a full change out, but it's incredibly responsive, and it has all of the embedded communications and control within it. So it's a very smart grid integrated hot water heater. So I just wanted to make that clear. HVAC unit, this is for DLC, pool pump, and then of course you have your smart thermostat for HVAC. And these all include installation, and the cost for the actual technology and syncing it up to the utility. So this is those average costs once again, which is great because the smart thermostats have come down quite a bit, even in just a couple years. So, the commercial DR site enablement. Once again, going to call out the obvious. We have this orange bar here that is the consistent, pretty consistent for $2,066. That is for this is to provide Shimmy type services, and it is the additional incremental cost for providing those services. So it's you have telemetry, network interface cards. You have typically you're going to need a gateway in order to gather the data at sub 5-minute intervals, and to package it up and be able to dispatch that over a communication infrastructure and get that back to an aggregator, to the ISO, or to the utility, so that they can actively monitor the performance of those end uses in that resource. And it does help, it meets the requirements of the ISOs and the RTOs, and these bulk power system operators require these more advanced telemetry. And that's one of the challenges for DR, is that it's trying to play in a space where telemetry and communication infrastructure has been built around generating resources and generation resources. And the other, you can see, as we just talked about, these are dollars per kW for enablement. So if you're going to work, so I'm just going to pick on refrigerated warehouses right now. It's a $289 per kW to enable that thermal load to basically respond to shift or shed signals. And so a typical refrigerated warehouse, could have discretionary load of, where we'll just make up 100 kW, and so yeah, you'd see a hefty price tag associated with that, but still worth it compared to a conventional generating resource. Then we've got all of this data on commercial lighting for demand response. One of the big hot topics in California is the Title 24 standards. The 2016 and 2019 have required that these lighting systems, anything that goes in there has to be DR ready and capable. And so this is really, we took a hard look at the different types of systems that could do and provide bulk power system services. As you can tell, it's pretty expensive. It's very expensive. They also, and if they're doing the Shimmy type service, they also need to have that communication infrastructure in place, and the energy management infrastructure and communication infrastructure in place in order to provide those. So this what we found too is the smaller, the medium retail and office buildings, the office in particular, are quite a bit more expensive than the retail, and that's because you have some different lighting intensity needs. Then we look at our industrial customers. The Shimmy, once again, you can see it pop out that the control for the communication hardware is pretty expensive per site. One thing to note on this is there's 3 groups here. There's one where it's shed, and that's just your DLC. It's a base switch on your agricultural pumping. The next group is where you can actually do shed and shift, and this is typically going to be, with some of the variable frequency drives using ADR, and then once again on the farthest side is with when you add the communication platform and the advanced resource interface to those systems in order to provide that service. So we're still looking at around $242 to $350 per kW for site enablement. And one of the things that we've heard throughout this assessment is this stuff's pretty expensive. And the reason that this looks really expensive, once again, is that we are attributing these costs to all to demand response, and that's there's plenty of other reasons. And anyone that's on the phone from the utility perspective is saying, yes, it is expensive. So the behind the meter battery, I have the following slide, which are electric vehicles. So these are sort of what we're calling emerging technologies. They're expensive right now. They're expensive enough to say, this is just not panning out quite yet. And so we're hoping to see these prices come down because these are very flexible resources that can provide pretty much all different types of bulk power system services. One thing that I want to point out here, and I think is important from this study, is we keep hearing about the value or the cost of batteries coming down over a period of time, and now, they're only $150 per kWh. One thing that we forget is there is a balance of system for the energy storage systems, and this includes permitting interconnection. We have inverters, we have converters, and specific power electronics that allow us to use that battery for demand response, or even just to interface with a solar panel. So it's not quite as cheap as we think it is, or that we keep hearing. And so that's really, hopefully that comes across in this slide, that we can you can see that, that there's extra components that we haven't necessarily talked about in the industry. And then we're finishing up here. I only have a few minutes left. This is for the electric vehicle chargers. One of the things to note is for this commercial electric vehicle charger for level 2 charging, these typically have more than one port on them. So they're going to have 2 or more ports, and still when they're automated, they are expensive. It's not with that ADR control and with communication and controllability, they still are expensive. So just some parting thoughts before we open up for a few questions. I apologize for running a little long. Energy efficiency, load modifying DR, supply DR. When we start thinking about integrating these, energy efficiency and demand response in particular, we can start thinking about how to make this stuff more cost effective. In particular, when compared to DR-only technology investments. Unfortunately, we have energy efficiency upgrade and opportunities for control upgrades, but we don't necessarily couple those with demand response. There's a host of reasons why. We're looking at some of that in another study that we're doing that should be coming out in the next couple of months. So I encourage you to check back in, and we'll be in touch on that. And then also the wholesale market design, but encouraging non-generator resources in wholesale markets. As I mentioned before, demand response is competing with generator resources and has to meet some of the same telemetry and energy measurement requirements that you would have with generator resources, and that makes it really expensive, in particular, since these are not generator resources. So great. And then the last slide here that I'll leave you with is, policy direction. Where are we going here? We have a lot of data now, and we can be making data-driven decisions and policy decisions, and demand responses certainly can play into that. I think that we have a need to catalyze shift services, which is that energy neutral demand response that can help absorb some of that solar generation during the day or wind generation, and move some load around. I think that demand side resources, we have the technology to do it. We just need to get the ball in motion and have an energy market actually that would support something like that. Distribution system automation, interoperability standards, all of these will help facilitate getting more demand response in the field and helping us solve some of these more complex problems that can't just be solved on the supply side alone. This is definitely a bigger nut to crack than thinking about how to handle this through renewables. Let's integrate them.